Good morning all. Now, in today's class we will continue with solving linear homogeneous recurrence relations. See the problem, solving an minus 5 into an minus 1 plus 6 into an minus 2 equal to 0 with initial conditions a naught equal to 2 and a1 equal to 5. This problem you have to solve. So while solving linear homogeneous recurrence relations, first find the characteristic equation. So first find its order. What is its order? Highest power is n, lowest power is n minus 2. So their difference is 2. So given linear homogeneous equation is of order 2. So character equation will start with square power. So characteristic equation is r square minus 5r plus 6 equal to 0. So we have to find factors for 5. Here we are having 1, here we are having 6. So for minus 5 we have to find factors. So we can write like r square minus 3r minus 2r plus 6 equal to 0. From first two terms take r as common. So we will get, that implies if you take r as common we get r minus 3 minus, take 2 as common, r minus 3 equal to 0. That implies r minus 2 into r minus 3 equal to 0. That implies r equal to 2 comma 3. So here we are having two real and distinct roots. So we know the formula. If roots are real and distinct, then general solution will be an equal to some constant c1 into 2 power n plus some constant c2 into 3 power n. Assume it as equation number 1. If initial conditions are not given, this will be the final solution. So if initial conditions are given, by substituting n equal to 0 and 1 in the given equation, we can obtain the values of c1 and c2. So substitute n equal to 0 in given equation. As anything power 0 is 1, right hand side will be c1 plus c2 equal to a naught. What is a naught here? A naught is 2. So c1 plus c2 equal to 2. Assume this as equation number 2. As we are having initial condition a1, put n equal to 1 in equation 1. So put n equal to 1 in equation number 1. Then we will get 2c1 plus 3c2 equal to a1. What is a1 here? 5. So we will get this equation. So c1 plus c2 equal to 2, 2c1 plus 3c2 equal to 5. On solving these equations, we can compute the values of c1 and c2. So first take c1 plus c2 equal to 2, second equation, multiply with 2. Then we will get 2c1 plus 2c2 equal to 4. See the third equation, 2c1 plus 3c2 equal to 5. Subtract second equation from first equation. c1 gets cancelled. We get minus c2 equal to minus 1. That implies c2 equal to 1. Substitute c2 value in equation number 2. Then c1 equal to 2 minus c2. That equal 2 minus 1. That equal to 1. So after solving the given equations, we got the constants c1 and c2 as c1 equal to 1 and c2 equal to 1. So therefore, general solution will be an equal to 1 into 2 power n plus 1 into 3 power n. This is the general solution for the given equation. As right hand side is 0, this is a homogeneous equation. So this is one of the methods of solving linear homogeneous recurrence relations. Here we got two real and distinct roots. So solution will be some constant into first root power n plus constant into second root power n. As initial conditions are given, by substituting in the solution, we will get the constants. Take one more example. So now we will discuss about solving non-homogeneous linear equations. So when can we say that the equation is non-homogeneous? If the equation is in the form C1 into an plus C2 into an minus 1 plus C3 into an minus 2 equal to f of n, where f of n is non-zero, then it will be non-homogeneous linear recurrence relation. So when we want to find solution for non-homogeneous solution, its solution will be in the form an equal to an power p plus an power h. What does an power h stand for and what an power p stand for? So an power p is the particular solution and an power h is the homogeneous solution. That means by assuming right hand side is 0, we will get some solution which is related to homogeneous part. It is denoted by an power h. Then we have to compute an power p, that is particular solution. So for finding particular solution for the given non-homogeneous solution, we have some conditions. So see the first condition, if f of n is a polynomial of degree q, that means if f of n is in the form some b0 plus b1 into n plus and so on bq into n power q. If f of n is a polynomial in this form, then particular one is not a characteristic root for the given equation, then particular solution will be a0 plus a1 into n plus a2 into n square plus and so on aq into n power q. That will be the particular solution. That means if f of n is in this form and if 1 is not a characteristic root for the given equation, then substitute constants a0, a1 and so on an in place of b0, b1 and so on bq. That will be the particular solution for that case. See the second case, if f of n is a polynomial of degree q in n and 1 is a characteristic root with multiplicity m. What do you mean by multiplicity? Repetition of the root. For example, m equal 2 means root 1 appeared 2 times. So if f of n is a polynomial of degree q and 1 is a characteristic root of multiplicity m, then particular solution will be like this, n power m into a0 plus a1n plus and so on aq n power q. This is for second case. See the third case, if right hand side is of the form alpha into beta power n, where both alpha and beta are constants and beta is not a characteristic root, then particular solution will be an power p equal to a0 into beta power n. So a0 into beta power n will be the solution if f of n is of the form alpha into beta power n and beta is not a characteristic root. See next case, if right hand side is in the form alpha into beta power n and beta is not a characteristic, beta is a characteristic root with multiplicity m. In that case, general solution will, the particular solution will be n power p equal to n power m into a0 into beta power n. For fourth case, if f of n is a polynomial in the form beta b0 plus b1n plus and so on bm into n power m into a power n and a is not a characteristic root, then solution will be like this, n power p equal to a0 plus a1n plus and so on am n power m into a power n, where a0, a1 and so on are constants. Last case, if f of n is a polynomial of the form b0 plus b1 into n plus b2 into n square plus and so on bm into n power m into a power n and a is a characteristic root of multiplicity m r, then particular solution will be n power r into a0 plus a1 plus a2 n square plus and so on into a power m n power m. So when we want to solve linear non-homogeneous recurrence relations, we have to apply any one of the following 6 cases. Here one problem is given, solving an minus 9 into an minus 1 plus 20 into an minus 2 equal to 1. As right hand side is non-zero, we can say that it is non-homogeneous. So for finding non-homogeneous solution, what might be the solution? 9 into an minus 1 plus 20 into an minus 2 equal to 1. So this is the given equation. As right hand side is non-zero, this is the non-homogeneous equation. So general solution for non-homogeneous reconciliation will be an equal an power h plus an power p. So first we have to solve homogeneous part. So first we have to compute an power h. So how to compute homogeneous part? First assume that right hand side is 0 and first find characteristic equation. So characteristic equation is r square minus 9 into r plus 20 equal to 0. Here 120, 5 into 420. We can apply 5 for here. So r square minus 5r minus 4r plus 20 equal to 0. From first two terms take r as common. So r common is say r minus 5 minus 4 into r minus 5 equal to 0. That implies r minus 4 into r minus 5 equal to 0. That implies r equal to 4 comma 5. So here we got two distinct and real roots. So what might be the homogeneous solution? Then homogeneous solution will be an power h equal some constant c1 into 4 power n plus some constant c2 into 5 power n. Assume it as 1. So first we have computed homogeneous solution for the homogeneous part. Now we have to compute particular solution. That is, we have to compute an power p. So how to compute an power p? Take right hand side. So that is f of n equal to 1. So 1 can be written as 1 into 1 power n. So it is in the form alpha into beta power n. So if it is in the form alpha into beta power n, and here 1 is not a characteristic root. So apply that formula. What is that formula? F of n equal to alpha into beta power n, and beta is not a characteristic root. Then particular solution will be a naught into beta power n. So by applying that formula, we can get f of n equal to a naught into, what is beta here? 1. A naught into 1 power n. Nothing but a naught. So we have to compute this a naught value here. Substitute in given equation. So substitute a naught in given equation. There we will get a naught minus 9 into a naught plus 20 into a naught equal to 1. That implies 21 minus 9, 12 a naught equal to 1. That implies a naught equal to 1 by 12. What is a naught? F of n. Therefore, f of n equal to 1 by 12. So, for the given problem, homogeneous solution is c1 into 4 power n plus c2 into 5 power n, and for particular solution, it is 1 by 12. So, finally, general solution is obtained by combining both. Therefore, an equal to an power h plus an power p. That is c1 into 4 power n plus c2 into 5 power n plus particular solution. What particular solution we obtained here? 1 by 12. So, an equal to c1 into 4 power n plus c2 into 5 power n plus 1 by 12. So that is the general solution for the given non-homogeneous solution. In this way, we can find solution for the non-homogeneous reconciliation. See the next problem. an minus 1 minus 6 into an minus 2 equal minus 30 with initial conditions a naught equal 20 and a1 equal minus 5. So, given equation is an minus 1 minus 6 into an minus 2 equal minus 30. That is the given condition. So what might be the general solution? General solution is an equal an power h plus an power p. So first we have to calculate an power h. How can we obtain an power h? By assuming that right hand side is 0, first we will find homogeneous solution. How can we obtain homogeneous solution? By finding the characteristic roots for the given equation, we can find. So characteristic equation is r square minus r minus 6 equal to 0. Factors for 6 are 3 and 2. We can apply here. So that implies r square minus 3r plus 2r minus 6 equal to 0. Take r as common, r minus 3. Take plus 2 as common, r minus 3 equal to 0. That implies r plus 2 into r minus 3 equal to 0. That implies r equal to minus 2 comma 3. Therefore, an power h equal c1 into minus 2 whole power n plus c2 into 3 power n. Equation number 1. So this is the homogeneous solution. Next we have to find particular solution. So how can we obtain particular solution? Take f of n equal to minus 30. So minus 30 can be written as minus 30 into 1 power n, which is in the form alpha into beta power n. Is beta characteristic root of homogeneous part? Here beta is 1, but characteristic roots are minus 2 and 3. That means it is in the form alpha into beta power n, but beta is not a characteristic root. So particular solution will be an power p equal capital A naught into beta power n. That means A naught into 1 power n. That equal A naught. Now substitute A naught in the given equation. So we will get A naught minus A naught minus 6A naught equal minus 30. A naught minus A naught gets cancelled. That implies minus 6A naught equal minus 30 implies A naught equal 5. What is A naught? F of n. That is therefore particular solution an power p equal to 5. So we obtain homogeneous solution and particular solution. Therefore substitute here. Therefore general solution is an equal c1 into minus 2 whole power n plus c2 into 3 power n plus 5. So this is the general solution for the given equation. An equal c1 into minus 2 power n plus c2 into 3 power n plus 5. But here initial conditions are given. So if you substitute initial conditions in the given equation, we will get constant values c1 and c2. So an equal c1 into 3 power n plus c2 into minus 2 power n plus 5. What is assume this as some number. So put n equal to 0 in the equation. Anything power 0 is 1. So c1 plus c2 plus 5 equal to a naught. What is a naught here? 20. So if you take 5 to right side, then we will get c1 plus c2 equal 20 minus 5. That is 15. You assume as 1. Next initial condition is 1. So put n equal to 1 in given star. So put n equal to 1 in star. Then we will get 3c1 minus 2c2 plus 5 equal to a1. What is a1? Minus 5. That implies 3c1 minus 2c2 equal minus 5 minus 10. Assume it as 2. So c1 plus c2 equal to 15. 3c1 minus 2c2 equal minus 10. For example, multiply first equation with 2. So 2c1 plus 2c2 equal 30. 3c1 minus 2c2 equal minus 10. If we add both, c2 gets cancelled. So 5c1 equal 30 minus 10, 20. That implies c1 equal 4. Similarly, then we will get c2 equal 11. Therefore, substitute here. Therefore, an equal some 4 into 3 power n plus 11 into minus 2 whole power n plus 5. So this is the general solution for the given non-homogeneous recurrence relation. Here some practice problems are given. We can do it. See the first one. an plus an minus 1 equal to 9 for initial condition a naught equal to 6. See the first one. an plus 5 into an minus 1 equal to 9 with initial condition a naught equal to 6. So first, what is the general solution? an equal an power h plus an power p. So first we have to compute an power h. So characteristic equation is r plus 5 equal to 0, because here highest power is n, smallest power is n minus 1. Difference is 1. That's why given is the equation is of order 1. That's why power will be 1. So characteristic equation is r plus 5 equal to 0. That implies r equal minus 5. We are having only one solution. Therefore, general solution will be an power h equal some constant a into minus 5 whole power n. Assume it as equation number 1. Next, we have to compute particular solution. So take f of n equal to 9. We can write 9 as 9 into 1 power n. That means it is in the form alpha into beta power n. What is beta here? 1. Is beta any characteristic root of the homogeneous part? No. That's why given equation is in the form alpha into beta power n, and beta is not a characteristic root. So particular solution will be an power p equal some constant a naught into 1 power n, which is nothing but a naught. So substitute a naught in the given equation. So we will get a naught plus 5a naught equal 9. That implies 6a naught equal 9. Implies a naught equal 9 by 6. That implies 3 by 2. So a naught value is 3 by 2. So combine both homogeneous solution and particular solution. Therefore, an equal an power h means a into minus 5 whole power n plus 3 by 2. Here initial condition is given a naught equal 6. So put n equal to 0 here. Anything per 0 means 1. So a plus 3 by 2 equal a naught. What is a naught here? 6. That implies a equal 6 minus 3 by 2. 12 minus 3, 9 by 2. So we got a equal 9 by 2. Substitute in given equation. Therefore, an equal 9 by 2 into minus 5 whole power n plus 3 by 2. So this is the general solution for the given non-homogeneous recurrence relation. See the next problem. an minus 7a n minus 1 plus 10a n minus 2 equals 6 plus 8n. Next problem is an minus 7 into a n minus 1 plus 20 plus 10 into a n minus 2 equal 6 plus 8n with a naught equal to 1, a1 equal to 2. So next problem is an minus 7 into an minus 1 plus 10 into an minus 2 equals 6 plus 8n with initial conditions a naught equal to 1 and a1 equal to 2. So solution will be an equal an power h plus an power p. So first we have to compute an power h, that is homogeneous solution we have to compute. So characteristic equation is r square minus 7r plus 10 equal to 0. We can write factors as r minus 2 into r minus 5 equal to 0. That implies r equal 2 comma 5. So particular solution will be an equal c1 into 2 power n plus c2 into 5 power n. Using as equation number 1. Now we have to compute an power p. What is f of n here? 6 plus 8n. So it is a polynomial b0 plus b1 into n into 1. Is 1 characteristic root? No. So f of n is a polynomial and 1 is not a characteristic root. So particular solution will be an power p equal capital A0 plus a1 into n. Here we are applying formula 1, that is f of n is a polynomial of degree q, and if 1 is not a characteristic root, then f of n equal a0 plus a1n plus and so on. Here we are applying that formula, an power p equal a0 plus a1 into n. Substitute in the given equation. So we will get a0 plus a1 into n minus 7 into a n minus 1. So wherever n is there, put n minus 1. 7 into a0 plus a1 into n minus 1 plus 10 into a0 plus n minus 2, a1 into n minus 2 equal 6 plus 8n. That implies expand this a0 plus a1n minus 7a0 minus 7a1 into n minus plus 7a1 plus 10a0 plus 10a1 into n minus 20a1 equal 6 plus 8n. Shuffle the left hand side so that constant terms will be one side and n coefficients will be one side. Therefore, a0 minus 7a0 minus plus 7a1 plus 10a0 minus 20a1 plus n into, from remaining terms take n as common, we will get a1 minus 7a1 plus 10a1 equal 6 plus 8n. So we will get minus 6a0 plus 10a0, 4a0. So 4a0 minus 13a1 plus 10a1, 11a1, 4a1 into n. 4a1 into n equal 6 plus 8n. Compare coefficients both sides. So 4a0 minus 13a1 equal 6. 4a1 equal 8. That implies a1 equal 2. So as a1 equal to, substitute here. So 4a0 equal 6 plus 13 into 2, 26. So 32. That implies a0 equal 32 by 4 equal to 8. So finally we got a0 equal to 8, a1 equal 2. Substitute here. So an power p will be a0 means 8 plus 2n. So particular solution will be an power p equal 8 plus 2n. So combining this with homogeneous part, we will get the general solution. In this way, we will solve linear non-homogeneous recurrence relations. In next class, we will see some more problems. Thank you.